Actually, the talk today will not be about formal concept analysis, but about another of my main research subjects, and it's situated in the area of logic-based knowledge representation. And probably some of you have heard about Semantic Web, about description logics. And the results I'm going to present today are about a certain description logic, which is very expressive, and a certain reasoning task, which is called answering of conjunctive queries. And I will try to explain or give a rough overview of what description logics are, what conjunctive queries are. And actually, what I want to start with is drawing a more general picture and talking a little bit about one of the major motivations why we actually do computational logic. So one of the motivations is to do knowledge representation. So you all know that there's a huge amount of knowledge available on the web, in companies, and people cannot really deal with this without help. So we need computers, and pure databases are not enough, so you need something more intelligent to actually deal with that knowledge. And that's actually what practical knowledge representation and semantic web research is wanting to do, and I will talk a little bit more about this. And as a next step toward the actual technical content of my talk, I would like to present what I consider to be a generic research methodology in logic-based knowledge representation. So if we do logic-based knowledge representation, what are the typical questions we ask, what are the typical stages of the research that we perform in order to obtain practically usable insights about knowledge representation. And this will actually take most of the time today. I will really go into details about this one result that I was already announcing, namely how one can establish decidability of conjunctive query answering for a certain description logic, which I will not bother to pronounce here, but I will try to explain intuitively in a bit. Okay, but let's start from the beginning, so to say. Knowledge representation, what is it about? Logic-based knowledge representation. So, I mean, the idea is, can we deal with knowledge in a formal way? Can we come up with general laws that allow us to actually systematically deal with knowledge and infer new knowledge from knowledge that we know in a way that avoids making errors? And that's actually not a very new question. That's actually a question which has been tackled since millennia. And one, for instance, finds in Aristotle's work examples of syllogisms. So where you have certain sentences and you ask yourself, just by looking at the structure of the sentence, which sentence would logically follow from that without even really analyzing the content, just structurally. And one could see this as a first attempt of doing computational logic. Then there was Leibniz, for instance, who said, oh, it would actually be nice whenever we had two people arguing about a certain case in science, when they just could sit down and say, oh, let's just compute it, let's just calculate it and see who is right. And that also, again, would require a formal system to deal with knowledge. So there's a very famous quote of Leibniz where he said, oh, it would be nice if you just could say calculemus, let us just compute, let us just calculate. Well, then there was a little bit of disillusionment in the 30s of the past century when it was known that, okay, mathematics is not really fully complete. There will always, whenever we have a system which is expressive enough, we always will have statements which we can neither prove nor disprove. That was Gödel's incompleteness theorem. And so a little bit people said, oh, now it's all lost and we cannot really get anywhere. At least we cannot really get the full completeness that we were actually striving for. But then still, with the rise of artificial intelligence in the 1950s and the ongoing decades, people would really try to at least put practical knowledge into formal systems and then work with that. And that's how expert systems, for instance, arose and how they were used. And so we still pursue this goal of getting or establishing ways of dealing with knowledge in a formal way, so that actually a computer could do much of the work that otherwise people would have to do. By this means, actually being able to manage the huge bodies of knowledge that are accumulated in today's society and in science and in many other fields. And actually, one of the strands that has been pursued puts into the picture the web as such. I mean, the web is a huge and interconnected body of web pages where you have information. And well, of course, primarily these web pages are targeted toward human users, right? They just look at it and they try to make sense of it by reading what's written there. But actually, it would be much nicer if we could enable computers to also draw this information and use that information and combine this information with information which is present on other web pages to make the most use of that big body of information that the web is. And this is actually one of the main motivations behind this semantic web research. And in order to arrive at this stage where really a computer could make sense or extract meaning from web pages, of course, the knowledge on the web pages has to be represented in a way which can be, well, worked on by a computer. Well, in this semantic web area, there have been quite a few standardization attempts where we say, okay, let's define how we actually can annotate web pages with information that is machine processable, machine interpretable. And out of these standardization attempts then arose OWL, the web ontology language, as one of the major achievements, but then also other formats a little bit below, RDF, the resource description framework, and RDF schema. Oh, sorry, I didn't want to go that. And then there's other formalisms which also play a role in this, what is called the semantic web stack, or some people also say the semantic web layer cake, because formalisms are layered on top of each other. Okay, and now that we have this, actually really industry and global players, practical players, start to really use these formalisms and thereby also really enabling this interoperability between different web pages, different websites. So this is really also, maybe you have heard about the term Internet of Things and, well, Web 4.0, what else is there? Open data. Also very important, where really all the also public bodies like governments are supposed to actually provide the information that it would have to be public anyways in a certain format, so that computers can make use of that. And the best practice to do that is actually in one of those semantic web formats. So this is really becoming reality, and now focusing on OWL as one of the most expressive already standardized formalisms that we have in the semantic web. It's actually based on a family of logics which have already been researched for 3 or 4 decades, and they are called description logics. So who of you has already heard of description logics? Okay. Oh, quite a few. Okay, that's nice. So maybe some of you know that they are sort of related to multimodal logics. So there's a close connection to that. And they are actually used to represent information in so-called ontologies are used to do practical knowledge representation. And there are tools out there that really can do reasoning. So you can really say, given that knowledge, and I have a certain question, can this question be answered based on the knowledge that I have formalized as a description logic ontology? And we have tools that can answer this question. Okay, that much about the foundations, why we are interested in description logics at all. And now let's focus a little bit more on what a typical research procedure or typical research methodology in logic-based knowledge representation would be like. So it typically starts from from a practical problem where we identify that we need a logic or we need to address a reasoning problem that is not yet covered by any of the approaches that we already know and that are already established. So we would identify desirable novel modeling and querying features and say, yeah, this is what we would like to be able to do. This type of question we would like to be able to answer, or this features we would like to be able to model in an ontology. Well, and once we've identified that, the question is, can we actually do it well? So one of the questions is there at all an algorithm that could do this task for us? Because there are actually logics which are undecidable, which means it's provable that there cannot be an algorithm that would answer all the questions of a certain type. And even if it turns out that a certain logic is actually decidable, which would be the good case, then we should actually ask ourselves, okay, so we can guarantee that there is an algorithm which does the job for us, but then the question is, how long will it take? How much memory will it take in the worst case? And that's when we have to investigate worst case complexities of those algorithms. And it turns actually out that, for instance, the newest version of the OWL language has a very high complexity, which actually also tells us that when we have a high complexity, not all is lost, because it could just be that the high complexity does not occur in practice. And that's why actually then the next step would be to try and design algorithms that would actually do the job, perform the task that we want to be performed. And then once those algorithms are designed, one would go ahead and implement them and do practical testing. And sometimes it turns out that the worst case complexity, even if it's seemingly rather bad, does not really hit us in practice. And at the very end, then one should also think of users. And one of the things, or the challenges in logic-based knowledge representation is that if we want ontology languages to be widely adopted by people and used, we cannot rely on them being trained logicians, right? That's a problem, because most of the people just would use those languages intuitively and would make modeling errors. I mean, we are working with practitioners in projects, and we are seeing a lot of modeling errors, which, I mean, you cannot blame those people for this when they are not really educated, because it takes some years to develop this kind of thinking. So what one would have to do is also to have those people in mind and develop tools that sort of allow an intuitive approach and allow intuitive modeling, avoiding the errors that normally would occur. That's a very challenging task, of course, but I mean, there are quite some promising approaches how to actually do that. Okay, so this would be sort of the chain of tasks that would need to be performed when one wants to extend or advance logic-based knowledge representation. And of course, I cannot talk about all of it today, so I will just focus on one very particular case where we actually try to investigate for a certain task, that logical question that needs to be solved, if it's decidable or not. So is there an algorithm that would solve this question for us? And the question that we're actually asking is if for a certain ontology, all the models would have, or would, I will explain it in more detail later. So if in a certain ontology satisfies or entails a certain so-called conjunctive query. But let's talk about this in more detail right away. Let's first talk about description logics. Even though the majority seems to be somewhat familiar with the term, it might be good to remind you of what we can express in description logics. And for the purpose of this talk, it's actually most helpful to think of description logics as a way to describe graphs. To be more precise, labeled graphs, and we can say a lot about those graphs. So let's look at this. So this would be a graph that we would like to describe. And graphs can be infinite, so that's not a problem. So we can assume that it just goes on and on like this. And so here, for instance, so one way we can talk about a graph is we can identify a node by its name. So O would be the name of this node, and there must not be any other node with the same name. But then we can also have like categories of nodes. So one category or one class, as we say, or sometimes we also say concept, would be A. So several nodes can have that property or can be in that class. And here we just say, oh, this one node, which is named O, must have an R connection. So R would be the label of an edge, an R connection to some node which is in the class A. And so we see, that's satisfied because this is our O node and it has an R connection to some node which is in the class A, right? And then we say every node in the class A has an R connection to a node which is in the class A. So we must have another one here and another one here. And so we also see that this is satisfied. On the other hand, every node which is in the class A must have an S neighbor which is in the class B. Okay, that's also satisfied. And then we have other things. We say that the edges which are labeled with F are inverse functional. What does that mean? So here we have such an edge, right? And inverse functional means just every node can have at most one incoming edge which is labeled with F, right? So what would not be allowed would be another incoming F edge here. That's what functionality or inverse functionality actually tells us. Same holds for the G labeled edges. And then we can make like Boolean expressions and say, well, whenever something is labeled with B or in the class B, then the node must be in C or in D. So we can essentially choose. And here we would have picked C. Here we could have picked D. So yeah, it's our choice. Here we just say that every C labeled or every node in the class C must have an F neighbor that is in E. So that again holds here, it holds here, and it holds here. So that's also fine. Okay, and every node in the class D must have a G neighbor that is in E, also satisfied. And then when some node is in the class E, it must either be in B or it's the one node that is labeled with O, the one special node. Okay, so this is how we can talk about graphs using description logics. And this small example already has all the features of this very expressive description logic that we investigate. In particular, it has the possibility to really speak about singular nodes. We call this modeling feature nominals. We can speak about inverses of edges. So edges, I mean, we have always directed edges, but we can also sort of talk about the inverse direction, about going backward through an edge. And we have a sort of counting. I mean, here we only have functionality, but this allows us to speak about how many neighbors a node might have, many neighbors of a certain edge type. So these are the modeling features, nominals, inverses, counting, or functionality, which together have typically had or cause some problems in description logics. So complexity increases if we have all three of them present. And actually for a long time, the problem that we considered, namely if conjunctive query answering is decidable for such a logic, was open actually. Okay, that much about description logics in a nutshell and very brief and just introducing the aspects of it that are of interest for us. Let's talk about conjunctive queries, so the other ingredient for our result. So conjunctive query is nothing else than, well, essentially a pattern telling us of a situation. So here the conjunctive query tells us, oh, there are three individuals where, so let's call them X, Y, Z. And we know that Y is married to X, and Z is a child of Y, and Z is a child of X as well. So essentially, it's a situation of a married couple with a common child. A conjunctive query can be easily expressed in SQL, for instance, and you could just submit it to a database and see if the database actually has such situations stored. And well, in a database, it's easy. The database could also be considered as a graph. And then we just look if we find a mapping of the variables into the database such that all the relationships are actually really present. So in essence, we look for a homomorphism from that query graph into the database graph. Okay, so and that's NP complete as a problem, but actually it's not so difficult. We just look into the database and see if we find this situation. But what does it mean to answer a query over an ontology? Because an ontology is not a database, and it's not itself a relational structure. It's actually a logical theory, right? And so what we typically then do is we look for safe answers. And that actually means, okay, assume we have the knowledge base over there, we have the query there. The knowledge base has many models, right? A lot of them. Typically, it's infinitely many. And also, on top of that, models might be of infinite size, which doesn't hold for databases. But then if we want to know if a query is really entailed by or holds for an ontology, we have to see if there is a mapping or a match of that query in each and every model of the database. So that's the query that's the question we are interested in, the task. Conjunctive query answering over an ontology. And that's, of course, much more difficult than just answering a query over a database. Because, yeah, as I said, we might have, typically we have infinitely many models, and typically models might be of infinite size, so it's not possible to go through all of them. Okay, so what can we do? Or how can we precisely now phrase our question? Well, our question is given a knowledge base of that very strange description logic, but essentially it just has all the features that I was introducing before. So that's just a description logic. And a conjunctive query. How can we find out if there is a match for Q into every model of the knowledge base? Okay, and so essentially, this should actually be an entailment symbol, but they have some symbols be replaced by the Windows computer. So this is how we could imagine what the algorithm should do. We input a knowledge base, we input a conjunctive query. It takes some time, but it will terminate, and then we get a yes or no answer. Yes, in case there is a match from the query into each and every model of the knowledge base, and no otherwise. So that's also what is written here. If we want to have a decision procedure for the query being true with respect to a knowledge base, well, we should have a procedure that terminates with output yes if it's the case, and terminates with output no if it's not the case. Now, by writing this up in this way, so we have here an entailment symbol, and we ask if the description logic theory, or we could also say knowledge base or ontology, entails the query. It tells us actually that this is a logical entailment problem, and luckily we know that entailment in first order logic is semi-decidable. And also luckily it's the case that description logics are a fragment of first order logic. So everything we can say in description logics we can say in first order logic. And also conjunctive queries are expressible in first order logics. It's just extensionally quantified conjunctions over atoms. So essentially this is this question if Q is entailed by K can be rephrased or is expressible as a first order logic entailment problem. And then, yeah, we can use the result of Gödel telling us that, well, we cannot really decide this question, but we have a procedure that will allow us to detect the case when the query is really entailed. Because first order logic consequences of a theory are recursively enumerable. What does that mean? Well, there is an algorithm, there is a machinery that would take some theory, take in our case the knowledge base, and would then just enumerate all the consequences. So it would give you one formula after the other, and all of the formulae would be consequences, logical consequences of our input. And it's not just the case that we get all we get is consequences, but also that every consequence will at some stage be outputted or output. This would give us a terminating procedure in the positive case, that Q is really a consequence, because then we just have to stand here on the other side and wait until Q comes along and then say, yeah. We have a problem if Q is not a consequence, because then we just would stand there, wait forever, but we could never be sure if we had waited long enough. So we can never be sure in the negative case. So that only solves part of our problem, the one part. What then needs to be added is how to test the negative case. So how to find out if Q is not a consequence of the knowledge base. Now, what does it mean that Q is not a consequence of the knowledge base? Well, it just means there is one model of the knowledge, there's at least one model of the knowledge base where the query does not match. And we would call such a model a counter model for Q. Now you could say, oh, that already sounds, we just check all the possible models, right? We just enumerate all the models and then we look into each of them if it's a counter model. That's a nice idea. The problem is that there are too many. There are uncountably many models that we would have to check, so we cannot enumerate them because there are uncountably many, so we cannot give them numbers. And a strategy to solve that problem is to say, oh, let's not look at all of them, but let's look at a subset of them. But the subset should have a nice property. The subset should be representative for the full set. What does that mean? It should be the case that whenever there is a counter model, an arbitrary counter model, then we also find a counter model in that nice subset that would make the subset representative. And of course, that subset should be countable, because then we would actually have arrived at something we can do. Then we could enumerate the subset and look for countermodels in that restricted set. And well, in order to be countable, you should at least have the possibility of finitely representing the models. And one candidate for such a nice representative subset would be regular forest-like models. Models which are not arbitrary graphs, infinitely size and arbitrarily complicated, but forest-like typically means, oh, you have some graph part, but it's finite, and then from that you only have trees growing, and they might be infinite, but they are really tree-shaped. So that's what we would call forest-like models. And now, that would be one hypothesis, that these models would be representative. But this needs to be proven, right? We really need to prove that whenever there is an arbitrary counter model, we find a forest-like regular also counter model. And the straightforward, or maybe not straightforward, but the direct idea how we prove such a thing is, okay, let's just assume we have an arbitrary counter model, and then let's think about how we can modify this or transform this, rebuild this into a model which has these nice properties, such that it's still a model and that still there is no query match. So that this counter model property is preserved while we restructure the model into a nice one. And that's essentially what we do. And that would be the big picture of our model reconstruction attempt. We would take the original model, we would do something which we call unraveling, which actually turns the model into a tree. And the tree would still be pretty modelish, but not really a model anymore. It would have some properties that would disqualify it as a model, but structure-wise, it would still be close to the model. Why do we do this unraveling because on trees we can always work more easily. We can apply algorithms more easily. And then the idea is to replace parts of the tree by other parts, by other bits and pieces, building blocks. And I will talk in more detail how to find them and how to do the replacement. And then we would actually do the reverse operation of unraveling. We would collapse, which actually repairs the unmodelish properties that we have introduced here and turns it back or tries to turn it back into a model. And that would actually do the job. So what we actually then end up with is indeed a forest model, because I mean, looking at the picture, we see a graph-like part, and then actually we have a possibly infinite tree, but it's really a tree. And it's not like here where the graph is actually infinite and it's not really a tree. And you cannot identify a finite graph part and then you have a tree outside that. That's not possible for this, but it's possible for that one. Okay, so that's the big picture. So how does it work in detail? So we just take our example that we had. I've already explained what all the formulae up there mean and explained that this would actually be a model of all the formulae, but it's not a nice one, right? It's not a forest-like one. It's more a ladder-like one, maybe. So first step, unraveling. So what we essentially do is we start from the named individuals, so from those nodes which have names, and we create such an individual, and then or such a node, and then we see what else needs to be included. Well, so the O labeled node must have an R successor, which is an A. Okay, and so we just add it over there as at the next level. And then, yeah, and so essentially we build the structure over there, making sure that all the statements here are satisfied. And whenever we have to decide what to actually do, we look here. We look into the original model, but by doing that, we create a tree-like structure, because none of these statements can actually force us to do a confluence. So whenever we have branched out, the branches never need to go back together. That ensures that we actually will end up with a tree. What, however, can happen is that the tree we create contains several elements or several copies of certain elements which actually should there be only once to have a proper model. That's why it's not a model over there. That's the only problem. That's the only problem, right? So, but you want the nominals to be nominals, to be really identifying. That's the only problem. Otherwise, it still behaves, it satisfies all the other axioms.
The only problem is this triangle?
The only problem with what we got here is that we have several copies of named individuals. So several green elements where actually there should be only one. And this needs to be repaired at some stage in order to turn it back into a model. But we can live with it for the time being. So that's what we call a quasi-model.
So yeah. Copies of other objects.
Yeah, but that would not violate any of the axioms. It's just when we say O, then we mean one element called O. And here we have, over there we have several O's. This structure would satisfy all the other statements. Okay. What would be the reverse operation? Just to see, okay, once we have such a quasi-model, how can we turn it back into a model? That's what we would call collapsing. And in a way, it's clear what happens. First of all, I mean, you have to identify all the green elements, right? So given such a tree, you would have to identify these two and put them together. But actually, that's not yet enough. Because if you do this, you might in turn violate functionality statements. So for instance, if you identified these two, you have actually you would create an element that has 2 incoming f edges, whereas our axiom says there must only be 1 for each. So actually, by trying to repair this problem with the nominals, we create a new problem with the functionality. And that's actually what then requires us to also identify these 2. And we have something like a zipper that happens here. So you have to go along all the chains and make sure that also the functionality constraints are satisfied. And that's essentially what collapsing does. First identify all the copies of the named individuals, and then make sure that functionality is satisfied by possibly identifying further individuals, further nodes. Okay, that would be collapsing. And now the question is, okay, what we actually are interested in is if a conjunctive query matches into a graph, right? That's the question we want to answer. But we will work mostly on the quasi-models and on the unfolded version of the graph. So the question is, how can you actually, by just looking at the unfolded version of the graph or the quasi-model, can you find out if there was a query match into the original model? And that's what we call entailment, so quasi-model entailment. So this would be the original model. This is a conjunctive query, which is actually rather boring. So that we could write it this way, and it just asks for 2 individuals connected by an R edge, where the second individual is connected with a third by an S, and so forth, and so forth. So this is the structure we are interested in. But when we actually look at the unfolded version, it might not be connected anymore. Because, yeah, looking at this, we have a part of the query matching here, a part of the query matching here. And then we have actually to be aware that due to the phenomenon that I just explained, these 2 individuals correspond to the same individual in the original model. And we could find out by identifying those, and then identifying those, and then identifying those. Okay, so that's why for conjunctive query, or matches of conjunctive queries, we have to come up with a bit more complicated criterion that not just makes sure that all the edges are there, but also that certain 2 nodes might actually be the same and might belong together. Okay, and so we have essentially these C1 and C2. These are 2 components, but individuals of the 2 components are connected by an equivalence relation that is established in the way I was explaining before. Okay, and now actually what I've already explained a bit is that, okay, these elements, they have names, and so it's clear they must occur only once. But then there are also other elements in our model, like this, for instance, which are also uniquely identified by how they are actually connected to a proper nominal. So this is like saying, I don't know, Aristotle, right? If we give a name to Aristotle, we know whenever we say Aristotle, we mean the same. But then we could say the father of Aristotle. So some individual is in a father of relation with Aristotle, which actually means, okay, since being a father, or having a father relation is functional, because every individual only has one father, the father of Aristotle is also a way to really identify one individual. And that's what we call new nominals, because they behave a bit like nominals because they are uniquely identifiable in the model. And new nominals can be found actually on what we call backwards counting paths starting from proper nominals. So that's exactly those where we have a nominal here, and then we have an edge here, which is actually counting or functional in the other direction. And that can actually be then iterated. I mean, we could also say the father of Aristotle, and that would be, again, an uniquely determined individual. So all these elements here are new nominals in a way.
Okay. And it's sort of clear that when you have the quasi-model, the unfolded model, and you have infinitely many new nominals in there, and then you need to collapse them all, you have no guarantee that you get a tree model back. So it will just be a tangle, a big infinite graph. So what we are actually aiming at is to remove as many as these new nominals, or the backwards counting paths, which give rise to the new nominals, from that tree-like structure. So we try to get rid of the backwards counting paths. And yes, that's what we try to do. And how do we do that? Well, we try to look at subtrees and replace them by uncritical subtrees, trees which give rise to less or ideally none or no backward counting paths at all. But the question is, okay, we can cut this out, cut this subtree out and remove it, but what to put in there instead? So it should still behave like a model because it's not allowed to violate any of the axioms or any of the statements that we imposed, because we want still a model to emerge out of that. And yeah, this actually brought us to the idea of how to construct such replacement parts of the model. And what we came up with was what we call the limit of a model. And that's a bit difficult to define, but actually the best way is to look at this example. So assume we have a tree, and we ask ourselves, is this a limit of the model? What would we have to check? Well, we would have to check if the initial segment of the tree, let's take the first two layers. If the initial segment of the tree occurs in the unraveled model infinitely often, and not just infinitely often here, but indeed with, or is caused or is created by infinitely many individuals or nodes in the original model. Sounds a bit strange. And this should not only be the case for the initial segment of, well, depth 2, but also for depth 3. Well, then we would get probably fewer individuals that would satisfy this property, but still there would be infinitely many, because we assume this model to be infinite there. And the same should hold for depth 4, and for depth 5, and so forth. That seems a bit contrived, but this way we actually can make sure that there are no backwards counting paths involved here. And so a limit of a model looks very much like a model, but in its entirety, it does not have to occur in the model. It's not really a subpart of the model, but every initial segment of it occurs often enough in the model. So that's why we call it the limit. I mean, the limit itself does not have to be present, but you can get arbitrarily close to it when you apply an appropriate tree metric, for instance, here. So that's the idea. And it turns out that these are the perfect replacements that we need. Because, well, the root of a limit never starts a backwards counting path. The limits of a model really look like a model. I mean, they locally satisfy the knowledge base. And that's why the idea is we unravel our counter model, we replace as many backwards counting paths as possible by those limits, and we collapse the result, and that should do the job. Okay, we have to make sure, what we have already made sure is that each of these operations would preserve modelhood, or at least quasi-modelhood. But what we still have to make sure is that whenever a query didn't match before, a query will also not match after this modification that we do. And in order to make sure that this really happens, we have to be careful when we do the replacement, which means we have before we replace, we have to look at the larger part. So we say, oh, I actually want to replace here. I want to cut out this whole tree and replace it by a limit. But you're only allowed to do this with a limit whose initial segment looks exactly like the initial segment of the subtree here. And the size of this initial segment is governed or is determined by the size of the query. Because that's the nice things about conjunctive queries, they can only look boundedly far. If the query has only 5 variables, you only need to have a distance of 5 that you have to make sure that it looks exactly like it looked before. And so that's what we do. That's what we call n-secure replacement, where n is the size of this initial segment. And now the big question that actually remains is this enough? So do we find enough n-secure replacements to really rebuild the model? Because it could just be we go through the model, we find a lot of backward counting paths, but we do not find fitting limits to replace them. And actually then the argument is, oh, actually we find enough. We cannot replace all of them, but we can replace enough of them so that only finitely many cannot be replaced. That is so the argument that we use for this is a bit related to the argument of Bolzano-Weierstrass, the theorem of Bolzano-Weierstrass tells you that whenever you have a bounded interval, or whenever you have a sequence in a bounded interval, then this sequence will contain a culminating point. And we can find this by just looking at the interval and then taking half of it and seeing, oh, either there's infinitely many elements up there or down there. Could also be in both, but okay. So we take one part interval where there's infinitely many, and then we can do the same and the same and the same. And so we find a culminating point. And that's essentially the same as here. So assuming we would have infinitely many elements where we cannot do a replacement, then we can use this infinitely many elements to construct a new limit that would actually allow us to replace most of the ones that we actually use to construct the limit. So that's a bit of the argument. It's interesting that we can use this idea from analysis actually in a completely different setting here. Okay. But the nice thing is that each such replacement step would not just preserve modelhood or quasi-modelhood, but it would also preserve the non-matches of the queries. And well, then what remains to be done is collapsing. We have made sure that that after this replacement, iterated replacement, of course, we only have finitely many backwards counting paths, which means we only have finitely many new nominals, which means we have only finitely many nodes which will end up in this graph part over here, which makes sure that after collapsing, we will have a quasi-forest model, or a forest model actually, which consists of a graph part which is finite, and then we have just trees growing out of it. Okay, now why have we done this? Well, actually the idea was to show that for each arbitrary counter model, we find a nice counter model. Nice meaning a forest model which is of this structure. And actually when we focus on forest models, the nice thing is we know regular forest models, so there's something else to be satisfied, but that's not so complicated. Then we know there's only countably many of them, which actually then brings us to the possibility that we have, we can enumerate all those nice models. Or we can enumerate all the forest models one by one, because they are only countably many, and for each of them we check if the query matches. And that means, since it's the forest models are representative for our purpose, whenever there's a counter model whatsoever, there will be a counter model which is in this enumeration, and that means that in case K does not entail Q, this procedure will terminate. And now what we actually do is we have two semi-decision procedures for the two cases. We can now run them in parallel. So we have one guy standing there, and well, either K entails Q, then Q will be enumerated by our initial procedure, or K does not entail Q, then a counter model will be enumerated by the other procedure. So when we couple the two semi-decision procedure, we obtain a decision procedure. The interesting thing is that this construction does not give us any idea about how long it will take. There's no complexity. Because if there were a complexity, actually one of the two semi-procedures would be enough, because then we could cut it up. So we have a decision procedure which could be theoretically implemented, practically it cannot be, or would not make sense to implement it. But we do not know how long it will take. It's just guaranteed to terminate, and that's all we know. So this is pretty useless from a practical perspective, but it's a very nice and deep theoretical result. And yeah, that's the first decidability result for conjunctive query entailment in a description logic which has all of these three features, which taken together are very complicated: nominals, inverses, and counting. And if one were to put this into the terms of modal logic, it would be hybrid multimodal logic with graded and converse modalities, for those of you who are interested in modal logic. Okay, this actually then gives us the insight that conjunctive query entailment for OWL is decidable under some mild assumptions. So what I haven't talked about is transitivity, because OWL actually also features the possibility to say that a certain edge must be transitive, and then queries can look arbitrarily far and everything breaks down again. But still, for a very big fragment of OWL, we could show that it's decidable. We still don't know any complexity. We know it's at least co-n2x time hard, which means double exponential non-deterministic, which is quite a lot. But when we focus on a certain type of queries which do not have transitive edges in their query pattern, then we can do it for OWL as well. So then we would have shown for this what we call simple conjunctive queries. It's decidable. For non-simple, we don't know yet. It could still be undecidable. Okay, and that's all. Thanks for your attention. I hope I did not stress your...
Thank you.
Yeah, okay, thanks.
Questions?
Yeah.
You said that some models can be erroneous, incorrect, or not consistent. And you also said that we check our queries against this set of models. And do we need to check whether they are consistent? How difficult is it?
You mean about this? So
when we have this machine,
yeah,
and we input our queries and test against a set of models.
Like this. This.
Maybe even the first one.
The first.
When we introduce this abstract machine.
This one?
Yeah, so
Okay, here we don't talk at all about models. Here we just talk about enumerating the consequences of a first-order logic theory. So that's purely...
So you
yeah.
mean earlier.
Earlier,
So just the first slide with this machine.
probably this one, yeah.
The previous one.
The-
Okay, so we check the query against all the set of models.
Okay, yes.
But may some of them be erroneous or inconsistent?
No, because a model will always be consistent. Okay, if the theory is inconsistent, we do not get any model, right? And then the query would be trivially satisfied. But that would be a corner case. I mean, that would actually be an easy corner case because it's easier to check satisfiability of a knowledge base or of a theory in description logics than it is to check a conjunctive query entailment. So all the models will be, I mean,
A model is not a theory, so
yeah. Exactly. The inconsistency of a model is a term that doesn't really make sense. A theory can be inconsistent, which means it does not have any model, but a model itself is a model and nothing else. And it's
just a graph.
yeah, it's just a graph.
Any other?
The conclusion,
Mm.
sorry, corollary that you made, was it known before? The simple conjecture.
I mean, with simple, we just mean conjunctive queries where none of the binary relations is specified to be transitive in the theory, in the ontology. That means simple. That's how we defined it. Maybe there's another definition of simple, but
That means once again that the relations are not transitive?
yes. So if we look at an owl ontology, you have the possibility to state that, for instance, you have ancestor of is a binary relation. And then you can state ancestor of is transitive. It's like functionality, so you can also state transitivity as a property of a binary relation. And if we say this about a binary relation, and then we use that very binary relation in a query, so for instance, asking for x, y, so that x is an ancestor of y, then the query can actually look arbitrarily far in the model, because it might just have 10 hops, like parent of parent of parent of parent of. And so this way we cannot restrict the area how far the query can look. And that break down this n-secure replacement idea, because we cannot select a big enough n so that the query couldn't look even further. But if we have plain conjunctive queries, we can only look so far as much variables we have, roughly speaking.
Yeah, back to this conclusion.
Mm-hmm.
So you role inverses relates to every function? Yeah.
I'm not sure. I mean, we do not really have function. We have.
Sorry, to every relation.
The question is just can we talk about going along an edge in the opposite direction?
Yeah.
And we can talk about any edge this way when we have inverses in our description logic.
So you must have all
You
roles
must-
should be inverse.
No. The roles can be just forward, but they also can be in inverse. If you have only inverse roles, then it's symmetric to the situation that you don't have any inverse roles. So then that would not be enough. So you actually must be able to talk forward and backward.
Yeah, but I don't get the condition. What's role? It's not.
Let's look at our theory.
It doesn't specify. Your class. Because you have more specific roles. That's it. Why should you speak about that?
I'm afraid I don't get the question. I mean, it's just we have this minus here, which allows us, whenever we have a role, to also talk of its inverse.
You're able to say that.
Yeah. I'm able to speak about the inverse of a role, which is another role which exactly goes into the opposite direction. And if we don't have this minus here, then actually things are much easier, and then conjunctive query
So
answering.
you can say that the role is functional.
Functionality is one thing, which, we have these three things. Nominals, which allows us to pinpoint at an individual and give it a name. Inverses, which allows us to go forward through an edge, but also backward. And counting. And counting, actually, functionality belongs to counting, to say how many neighbors of a certain type a node may have. Functionality means at most one. And this is quasi a combination of inverses and functionality. That's why we call it inverse functionality. It's stating that not the binary relation itself, but its inverse is functional.
So it's not full counting power here.
No, actually functionality is enough to already make it very difficult. Let's put it this way. That also depends on what other modeling features you have. So we were also assuming you can have like Boolean combinations of roles of a certain type. That's what I omitted because it was not important. And if you have that, functionality is actually enough. Then you can construct all the other counting quantifiers, so to say, using a combination of functionality and the Boolean combinations on roles. But that would go too far. But yeah, you're right. I mean, functionality is already enough to make it complicated, make it that complicated as I presented it. So if you have anything more would then not be more difficult than that.
So what can you count there in your language?
Well, we always count neighbors, right? Neighbors of a certain type. So we can say, do we have a nice example? No, but we can say, I have at most 3 friends which are PhDs. Things like that. So that's typical statements one can express. So it's how many elements there are connected via a certain type of edge that then are also in certain categories. That's the typical, that's qualified cardinality constraints, as we call it in description logics. There's a question? Yeah.
Are there any limitations on the variance? Do you define the rules maybe?
So, I mean, the limitation is that it's conjunctive queries. And a conjunctive query is you have atoms, which might carry individual names or variables. And then you have a conjunction over those atoms. And then you might existentially quantify over some of those variables. Or actually, you quantify over all of them because we were looking at Boolean conjunctive queries. That's the type of query we are looking into. And I mean, for the result to hold, none of the predicates, of the binary predicates that we use in the conjunction is allowed to be defined to be transitive. So that's the class of queries we look at. When we allow transitivity, we don't know anything. Could be undecidable, could be decidable, it's still open. And the same when we go to more expressive types of queries, because there are also queries which can be defined by means of logic programs, for instance, and then we also don't know anything about it.
And also, I want to ask, can you tell about the real examples?
That's why I said it's a very nice theoretical result, but practically, I mean, it would be nice to have a quick algorithm that solves this for you, but so far, I mean, the algorithm I presented is pretty dull, right? I mean, you just enumerate all the consequences of a logical theory. I mean, you can do this applying the deduction calculus of first-order logic, but then this is the opposite of goal-directed, what happens here, right? You just wait for the right consequence to pop up.
Okay, maybe what type of system? Or which systems? Informational system?
I mean, it's related to ontologies, right? The question is, I have an ontology, and I want to know, is there any evidence in the ontology which allows me to infer that there is a married couple with a common child? And it's not that it should be explicitly stated in the ontology. It can be inferred through many axioms working together. And that's the big challenge, actually.
Okay, maybe they're multi-agent systems.
Oh. For multi-agent systems. I think multi-agent systems are somewhat orthogonal to this knowledge-based approach. Of course, you can say we have many agents, and each of the agents has his or her knowledge, and they might be confronted with queries coming from the other agents, but
They need to exchange data.
right.
And they need required effects, and then these effects you can get from ontologies.
Right. And if these facts are supposed to be acquired using conjunctive queries, which makes sense. I mean, sometimes you just want to know which married couple with children do you know? And you just want to have all of them given to you. Then you can formulate a query and ask an agent. But then the agent would have to do the reasoning that I was describing. And that would take quite a long time if nobody comes up with a better algorithm. So there's a lot of things to do. We just did this decidability study to show there can be an algorithm. The other possible outcome would have been it's undecidable and it doesn't make sense to at all look for an algorithm. So that's why this is the first step. When we first want to find out if it all makes sense to try and look for an algorithm that does the job for us. And here we say, okay, there is an algorithm. Ours is not really practical, but maybe somebody else finds a more practical algorithm. Let's see.
Why this particular logic?
Well, because it's essentially, it's almost OWL. And OWL is a standard. It's a standard knowledge representation representation language used in all kinds of environments. So it's a standard ontology language. That's and it's sort of it's a bit sad that for the full OWL language it's still open if it's decidable or not.
And what's missing to be full?
What is missing is transitivity. But the problem is our approach, or the transitivity destroys our approach. So if we added transitivity, we would have to start from scratch. And this was already hard enough. It took us 3 months of focused work in Oxford. And I mean, people had tried to do this before for years. But yeah, from then on, no complexity result. We actually waited if there's something more that can be learned about this. And we only have this lower bound, complexity-wise, that it's co-n2x time, which is, yeah. But it could still be much worse. It's just a lower bound. Could be non-elementary. We simply don't know.
Are there cases of constrained transitivity? Just only one relation?
That's a good question. Not that I would know. Of course, you can have transitivity in the knowledge base if you, which already has quite some effects inside the knowledge base, if you don't use a transitive relation in the query. That we still can cover this case. So it can be, you can have transitivity in the knowledge base, arbitrarily many transitivity statements. But we cannot handle the case where this transitive predicate is used in the query. That's the problem that we have.
Sorry, and you described the language, but query is a richer language.
Well, I wouldn't call it richer. A query is really, I mean, here we don't, yeah, it's a set of atoms.
A set of atoms.
And they are meant to be conjunctively combined. So the commas are conjunctions. And then we actually assume all the variables to be existentially quantified.
Oh, yeah,
So we just say, are there x, y, z such that this structure is somewhere in the model?
So you may have cycles in the query.
Yes. And only if you have cycles in the query, it's really a problem, because otherwise, if you have non-cyclic queries, you can reduce the problem to satisfiability.
To have cycles in the language?
Well, in DLs, DLs are structured, and DLs don't have variables to start with, right?
Oh,
if you
yeah,
look at,
yeah, they don't have variables.
And so essentially every structure you talk about must follow the term structure of the expression that you have. And so you can only talk about trees in a way.
More questions? Thank you.
You're welcome.